All right. Thank you guys. I'm really excited to be here. I want to start by saying thank you for having me here and for giving me accommodations and inviting me to this beautiful city and this beautiful country. It's been years since I've been to Warsaw. As you see, I'll be speaking about Haskell and about the arrays, about particularly the library that I've been working on for a while and got a chance to release it earlier this year. I want to warn that this talk is going to be in English, just because it's easier for me to speak in that language, except the first couple of slides. Nazywam się Alexey, jestem z Białorusi, pracuję teraz w firmie FP Complete. Studiowałem w Uniwersytecie w Nowym Meksyku w Stanach Zjednoczonych, więc mieszkałem tam przez 12 lat. Ale zacząłem studia tutaj na Uniwersytecie Warszawskim, więc rozumiem polski język. Jeżeli ktoś ma pytania, może spokojnie zadawać w języku polskim. Nie obiecuję, że zrozumiem, ale postaram się. To jest moje zdjęcie 14 lat temu na lotnisku w Warszawie. To byłem ostatni raz, kiedy byłem tutaj w Warszawie. Więc bardzo jest przyjemnie mi tutaj być z powrotem. So, that's where I will start in English. If you look at the package, if you search for array, there is like 80 results. There is a crap load of stuff that deals with arrays, and it's the most common array package, which is wired in base. There is a vector that is extremely popular and very known package. Everybody uses it, and I suggest to do so. There is also Repa, Accelerate, and others. So why would we even implement another library? Why would I even work on it? So first of all, I want to ask if anybody has actually used Repa or Accelerate. Okay, good. How about Vector? Okay, good. Array, I don't even recommend you using it because it's just a terrible way to deal with arrays. So what is an array? This is going to be basically my definition. Don't expect you to believe me. But an array is obviously, it's a data structure. It's represented in the library by type family, data type family array. And array is also, it's a mapping from an index to an element, which is, here's an example function from our library. And an array also has some sort of size or shape. So there is a whole bunch of different array types. You all programmers, I'm sure you've dealt with a lot of them. There is one-dimensional vectors, which are the most common ones. There's two-dimensional matrices, rectangular, and dimensional, which is the most general case of the previous two. Those are the arrays we're going to concern ourselves in this talk. There is reged, jagged arrays, sparse, tote, and Judy. I'm planning on having some support for reged and jagged arrays in the future, but it's very limited right now. I'm not going to be talking about that. So let's look at the array data type or type family, if you wish. The end is a type of an element, which is going to be stored in the array. Then the index of the array, which will dictate the dimensionality of the array. And a representation type. For those that have used Repa, they're familiar with it, they will be very familiar with this definition of the array. For those that don't, I will be talking deeply about it, so don't worry. First of all, we'll start with an index. This is vastly different. I don't know anybody that has this kind of approach to indices. Well, Repa has something similar called shape and stuff, but what is an index? Index is something that we can convert to a flat index, which will allow us later on to index an element inside of the memory. So we have a few helper functions that will convert to linear and from linear. It also dictates dimensionality of the array. So how many dimensions we're going to have? 1, 2, 3, or infinitely many. No, not infinitely, but n dimensions. That's what the ren comes in. And for index to be used in a REPL library, it also you should be able to increase and decrease dimensionality in order for you to be able to work with arbitrary dimensions. So that's why there is helper function like cons and snock and cons. First of all, I want to tell you that in order to use library, you don't need to know all this stuff. This is just a backend implementation, but it's good to understand it in order to be able to write a better code. So what is an instance of an index class? Obviously, the first one is int, which can be used for flat vectors. And then I started using tuples at the beginning, and you can still use them. There is an instance for this class for tuples of ints up to 5 tuple. And there is type synonyms, located one x to t, which you'll see why they call that way. There is also a type family lower, I guess I could show it like that, that allows us to describe a dimension of an index that is lower than the one we're talking about. Like here, we have a cons, which takes an int and an index of lower dimension, and it will give you an index of this dimension that we're interested in. Everybody knows what cons is, right? No, it's something that you can add on top. With lists, it's very popular. It's not important. So what is an index, the proper way to index that we do in massiv? First one is the ix0, it's a 0 dimension. For arrays, it's kind of useless. It's an array can be only empty or has one element, which is basically a scalar array. It's here purely for type inference, and it's not used directly. You can only sometimes see it in GHC compilers. There is an ix1, which is an int, index of first dimension. Index of second dimension is constructed with this cute little colon dot, which takes 2 ints and construct a 2-dimensional index, and n-dimensional index. This is the important one, which allows you to construct an index of arbitrary dimension. It takes an int and an index of lower dimension, and we'll construct an index of dimension n, which is a type level natural number. And this type family that relates them all together, which allows us, oh, by the way, here is, yes, the lower definition. If you don't know what's a type family, it's not too important, but it relates them. ix1, the lower of ix1 is ix0, lower of ix2 is ix1, lower is ixn, it's ixn minus 1. It kind of goes down, yes?
I mean, obviously, you don't usually work on really high dimensional arrays, but do you get any kind of slowdown or problems with like high dimensions and that kind of code?
It will get slower. It's obviously because you have to do a conversion from all these nested dimensions into a flat index. But sometimes we actually do need, even if it's a very small array with, I don't know, a million elements, you can construct many dimensions of a million elements. So, particularly, let's say 6, right? Of 10 by 10 by 10 by 10 by 10. Yes?
Is the special case for 2 dimensions for convenience?
Yes.
Only?
It's not for convenience. It's the special case in REPL, let's say, is Z. It's a 0 dimension. I wanted to avoid Z. I don't want to avoid 0 dimension completely. Okay. If we want to use first dimension as the base case, it's ambiguous because it's an int. We never know what the base case is. So the next available one is the second dimension, which becomes the base case. Okay. And here is what it allows us to do. And the best part about it is it's unambiguous. Whenever you use tuples of many, 5 tuples of whatever, those are ambiguous. With this, you lose that. The only ambiguous index is an int. So you can construct 8-dimensional if you want, 3-dimensional, and there is a lot of dots here, so it's kind of hard to parse. Let's see, oh, I can point like that. That's much better. Here's the base case, the second dimension. There is the third dimension, which uses the base case constructor, and then the smiley face. And this smiley face goes all the way can construct basically as many dimensions as you want. So here's the benefits, right? IX0 is no longer of interest to us. Like, this is the way to construct an IX index of first dimension in repo. You do a Z, and then you do this operator, and then an int. You have to carry it around. It's very inconvenient. In massiv, you can just use an int for indexing vectors, which is really nice, I think. Then the cool part also, all of this IX is an instance of a bunch of classes like num, ord, eq, and even unbox. So you can do cool operations, like you can treat them as numbers. You can multiply them, you can sum them, you can divide them, and you can compare them, which is extremely convenient when you write actually code. It's a lot less bloated. So there is if people don't like these operators, or they don't want to turn on the extension, a few extensions that are required for operating on those indices. There is convenience constructors, though, which are pattern synonyms. If you're not familiar with them, it's not too crucial, but you can actually avoid this ambiguity on IX1 on the int. If you wrap around with the constructor, which is actually still an int, you can treat it as for all purposes an int, but it will drop that ambiguity. Because, like, if you type it in GHCA file, all it knows about it it's a num, right? And if even farther, IX1, IX2, IX4, whatever, and you can pattern match it back, so you can unwrap indices in the same way. So I, J, K will be 1, 2, and 3. And there is also helper function for converting two tuples and back from tuples. Sometimes they come in handy. Indices, what's fun about that? Let's construct an array. I usually import it not qualified, but just as an A, because there is some collision with functions like map and zip width. So here's the function that allows you to construct an array. It takes as an argument a comp. I'll talk to you in more detail about it later. And it takes a size, which is what I was telling you about. Array has a size and a function that maps an index to an element. So this will construct an array. It's similar to a vector library. Has a function called generate, which gives you an int to an element. Yes?
Just to be super sure, this is an n-dimensional index.
It's an arbitrary dimension, yes. The size that you'll give it and the function will dictate the dimension of the array. So yes. This is make array in action. We construct an array of size 5, and each element is just a multiplication of its index times 10. So we get a one-dimensional array. Over here we can see all of a sudden the index is 1, the element is int, and the representation is d, which people who are familiar with the repo know about. I'll talk about it in a moment. And it gives us an array. It has a little pretty printing, which is very convenient. I find like I got those ideas from MATLAB, I think. You want to be able to inspect your array. So not everybody thinks the same way, at least from my experience. Here is we construct a two-dimensional array. Again, there is a seq, there is a size of the array 3 by 5, and there is a mapping from an index to an element, which is a multiplication of this index. Here I had to write it in 2 lines of code just because make array is ambiguous in its type. It doesn't know the representation, so I'll talk about that in a little bit as well. But here is this two-dimensional array. That's what we wanted. So what is the delayed representation? First, before I go into this slide, I want to say that functional programming is amazing. It's an amazing paradigm, but it has a little bit of a drawback. Whenever you, let's say, map a function over it, theoretically, you're supposed to allocate a whole big chunk of memory again for this new array. And this allocation of memory is extremely expensive. So GHC and library authors, they came up with cool trick ideas to avoid that. This is one of those cool trick ideas to avoid memory allocation. So in functional language, we can represent, actually in any language that function is a first-class citizen, we can represent an array like that. Array is something that has a size and a function that maps a size to an element. So we can wrap that information with a data type. By the way, this code is not part of the library. It's just an introduction of what a delayed array is. So here's how we can make an array. There you go. You can give it a size and a function, gives you back an array. We can pull out the size, great, and we can index that. So we can give it an array. We can give it an index that we're interested about, and we're supposed to get back maybe an element because this can be out of bounds, right? So that's what we do here. We say check if it's safe. Okay, we return just f applied to that index, and this will return us an element. Now, this is safe function. It's not really correct, but it's good enough for demonstration purposes. The problem here. Well, let's talk about not problems, but the good things about it first. What can we do? What can we do with this? You think it's very limited. It's just a function and an index, but no. We can make it an instance of a functor, so we can map functions over it because it's a function. We can map an index-aware function right here, f and g, and we simply compose those functions like here, like here. This is just a composition. So this is a way to fuse that computation. We can join those functions in one little long computation, and at any point here there was an allocation in memory, which is really cool. The problem with this is if you construct an array like this, you get an array, you do those operations. You multiply, you zip them, all sorts of zip them with an index. If you do an index, it will return you an element. But if you do an index at the same location again, it will perform the computation again. So there is no some magic memoization over here. It will do the computation again and again. So if it was that fused computation was extremely expensive, you get extremely bad performance. I cannot stress this enough because that's the first thing that NoMS users get tripped over. I've been there, and they say, why this code is so slow? We got to watch out really careful. But I did a little trick. I disallowed indexing on the delayed arrays. So just to prevent users shooting themselves in the foot, if you try an index, this, by the way, this is already code from the library. So here we construct an array, a one-dimensional array. It's a vector. Here's the expensive computation. It's been fused. So here's an array that is fused. We try to index it. We get an instance error, compiler. If you still want to index it, there's a function that lets you evaluate this particular index, and it will give you back the element. But it will do that so every single time you try to index it. So another pitfall I want to say right away is if you take the delayed array and the same delayed array, and you try to zip over with a function over it, this will perform the same computation here and here. It's okay to zip two different delayed arrays because that computation will be fused, but not the same array. How do we go from delayed array to manifest array so we can actually treat the array as a normal, regular array that we are used to, that is represented by a regular stuff in memory? We can either construct it the same way as we were constructing delayed arrays. We use make array. Oh, by the way, this function make array R allows you to pass over that representation, and the representation in this case is P. Before it was D, which stands for delayed array, and P stands for primitive. I'll talk about those in a little bit. We can construct a manifest array. In this case, this array can be indexed in constant time, and this stuff is in memory. And we can go ahead and index it. Another way to go from a delayed array into a manifest array is to compute it. I'll talk about what does it mean, the actual action of computation. But here, we take a fused array called compute, and now we can go ahead and index that array. Does anybody have any questions? Does it make any sense? Okay, good. If you have any questions at any time, just go ahead, yell out, don't hesitate, don't be shy. So how can we do a computation? We have a delayed array in one side, and we have a manifest, the goal that we want to get to. What we can do, we can compute each element of the array and then load it inside of the memory. That's the actual action of computation. If you've never done mutation in Haskell, it's ugly. We try to avoid it, so we do until we have to actually do mutation, and in this case we do have to. We take a pure array, we thaw it, we do all sorts of mutation in it, and then we can go ahead and freeze it back and treat it as a pure, nice data type pure array. And this type class is required in order for.
So whenever you thaw it, it allocates the whole array in memory, right?
If you have in this case array R, it's already mutable. So this array is already represented in memory. It's already in memory. If you call unsafe thaw on it, all it does is it just unwraps it. If you do a thaw, a safe thaw so-called, in order to keep the referential transparency, it will make a copy of that array, and then you can do mutation on it, and then you can freeze it, and it will be a totally different array. So that's why it can be safe. If you do unsafe thaw, it just unwraps, and it's a terrible way. You as a programmer, if you use those functions, you have to guarantee referential transparency yourself. That's why they're not exported by default, and you normally, as a user of library, you don't use them unless you be ready to shoot yourself in the foot. The only reason why I even mentioned that stuff is because I want to explain the actual hierarchy of classes. That's the crucial part. We already learned manifest. Manifest is the array that we can index in constant time. It's represented by memory. Mutable is the one that we can mutate. And all these 5 representations, they are mutable representations, and they as well manifest, so we can index them. Let me go one by one what those representations mean. Not in order. Here is the primitive array. Primitive is a type that can hold any primitive elements, actually. Primitive elements will be like char, int, double, float, stuff of that nature. Anything basically that is an instance, I lost my cursor. Anything that is an instance of a prim class from a primitive package. They are backed by a byte array. If you don't know what it is, don't worry about it. It's a primitive in GHC. The most important, it allows you to give, it gives you direct access to memory, so you can do fast reads and writes. Indexing is fast, it's cache friendly, it's garbage collected, so we don't need to worry about losing memory and stuff. The one drawback is it's not safe with fast foreign function interface, the FFI. So you cannot pass it to C or other languages. Then we have boxed arrays, which are slower, obviously, because they are just arrays of pointers that point to actual values. So there is a level of indirection which makes them slower. They're backed by array hash. The great part about them, they can hold any element, I mean any data type that Haskell can come up with. Functions, if you want, even other arrays. The elements are strict to weak head normal form. If you don't know what it is, by the way, how many of you do know what weak head normal form means? Okay, good. Haskell is a lazy language. Any data type is going to be just a thunk. boxed arrays, they will make sure that elements, they are evaluated. So whenever you call compute on a delete array, it will create an array of pointers. So those pointers will be evaluated, the structure will be evaluated. And as we have here an example, this function f of I, it returns nothing on even and just I on odd, right? We create an array like that. Cool, we have an array of nothings and justs. Now, if you try to index this, if you try to think about it, the array is evaluated to the point that it knows that at any location there is a nothing or a just, but it doesn't know what values that the just will hold. So that's what weak head normal form means. It's strict but up to a point. Now, in order to demonstrate an example that the array will be evaluated up to weak head normal form, the structure of the array is evaluated. We create an array of very small size 3, and the elements of the array will be 5 divided by the index. Obviously, the 0th element will be an error because it's the division by error. But even if we index the first element, it will throw an error, because we'll try to divide by 0 for the previous element. Now, if we try to compute this in parallel, if we try to create this in parallel, well, all it's going to do is it'll create a bunch of sort of thongs. And it's not a real parallelization. For that, there is an N representation which stands for normal form, which means every element will be evaluated all the way down. Whenever you create an array, every single element will be evaluated up to NF data class instance. That's the requirement. Every element is supposed to have this instance, NF data. Here's the demonstration. What's the difference between the B and N representation? Here's what we had before. If even, nothing, good. But then if it's an odd number, we'll have a just undefined, which is it's a bottom. It will throw an error if you try to evaluate it. So with the boxed array, if we index this boxed array at an even location, it will give us nothing, which is cool. If we try to index at 1, it will evaluate it and it will give us an error. With the normal form representation, if we try to index an even location, it will give us an error because it will evaluate all of the elements all the way down, which is extremely important if you try to parallelize this computation. This, not particular because it's very, very cheap. Next representation is Storable Race. It's a kind of sibling of primitive because it's also backed by a byte array, but it's a pinned byte array. So garbage collector is not going to move it around. So once it's allocated, it will stay in this place, and it will be safe to pass it to C function, for example. So it's safe with FFI. It's just as fast as primitive. It will hold any element that has an instance of storable class. It's fairly easy to make your own instance of storable, which is great for extensibility. It is the subject of fragmentation. So like garbage collector for primitive arrays, if there is a bunch of small chunks around, if it's losing memory, it will rearrange it and to keep fragmentation in check. With storable arrays, this is not going to happen because it's guaranteed not to be moved. But it's okay usually with arrays because they are pretty big anyways, and we don't expect a lot of fragmentation there. There is unboxed arrays, which is just a cute way of making arrays of arrays for complex types. Like let's say if we want to store a tuple, well, tuple is not a primitive type, so we cannot use a primitive. But we can do an unbox. We can go ahead and wrap this array and represent it as 2 arrays of primitive types, as you can see here. This is a nifty trick that it's not done by massiv, it's done by vector package, and it's actually a class from vector package. We just support it here in massiv. So same property as primitive, elements have to be in unboxed, have unboxed implementation. Now the interesting part comes in. Everything up to this point mostly was just an introduction to Haskell. Yes, the exciting one. We have computation strategies. Sequential computation strategy, which will compute stuff on one core. There's parallel and parallel on. We'll do parallelization across all available cores, available capabilities if you wish. And par on, you can specify which capabilities you want to use. Capability is a Haskell way of saying, GHC way of saying, use this core. So,
can you do it on CUDA?
Say it again?
Can you do it on GPU?
Ah, that's a great point. Unfortunately, no. I don't have enough experience with GPU, and it's not just-in-time compilation like what Accelerate does. It compiles it, or it uses a little VM backend to create code. Massiv uses nothing but GHC. There is very minimal dependency footprint. My goal in this library was to make it usable for everybody, not just people who have CUDA installed and all VM, right? It has which representation?
REPA integrates with Accelerate. It has the array representation for Accelerate arrays.
It's a little bit different. I think it's Accelerate. You can use the REPA as a backend. That's what you mean, right?
No, I think it's the other way around.
Possible. I don't know. We can discuss that a little bit later. I don't know. I'm not familiar with that particular. Although I remember seeing that A representation. It's a separate package. I remember seeing it. I don't have much detail on that. It'd be a good idea to implement it because it's just as well. It's even better extensible than repase. We can create a representation that would use Accelerate, but at the end there is a benchmark against against Accelerate. I don't want to spoil it. Let's go for it. Construct. That's another type class in the hierarchy. Anything that is an instance of construct can be constructed. This kind of array. It's an unsafe make, but don't worry about it. And you can also get computation strategy and set computation strategy on the array. There is a size constraint, size instance. This is the type of arrays that can be resized and extracted. Excuse me. There is another important one is the load array. This is the array that can be loaded. Delayed array is has the instance for this class, and this is the bread and butter of parallel computation. It's a way to describe for representation how it's supposed to be loaded into memory. Not only which elements, how it will be loaded, because you have all the information you need. You have the array that you want to load into memory, and you have two functions that will allow you to read the array that you're trying to write to, which is not really used right now. It's not necessary. It's for future compatibility only. And there is the function that allows you to write into the array that is being created. So load S is obviously we'll do it sequentially. Load P, we'll do it in parallel. That's why there is a difference in monad. This is an arbitrary monad, this is an IO monad, because if you want to do concurrency, you have to leave an IO monad. And it also takes a list of capabilities that you want to use for parallelization. There is a scheduler, a custom scheduler implemented in Massiv that will do the parallelization for you, which is really, really cool. But it's sort of complex. It's a topic of a totally separate talk, I would say. So I'm gonna skip over that. This we can discuss array to load. yeah, just what I said. This is the actual right element. Why do we need that? In order to construct and compute arrays. Here's the function that we already seen. Make array. Now we know already everything that is on the slide. Make array, anything that is constructible can be created, any array. It will take a representation, one of many representations that I've mentioned. It will take a computation strategy, it will take a size, a function it will construct it, and it will give you back an array. There is also a function compute as well as sibling function that will differ very slightly, like compute source, compute int, read the commutation for any differences, but the whole concept stays the same. You give it a representation that you want, which can be any mutable array, and you give it any array that can be loaded. And we'll load that array into memory, and we'll give you a manifest representation of this array. And the cool part, it will do it in parallel on as many cores as you have, and it'll do it so automatically. You don't need to worry about deadlocks and any of the concurrency nonsense, because as you see, this is guaranteed to be referentially transparent. There is no model in here. It's a pure function, which is really cool, I think. It does some trickery underneath that is like unsafe perform I/O, but you have no way around it. The library does guarantee the referential transparency. That's how the world works, I guess. So here we create make array, delete array. We want to parallelize it on 7 cores. And we create a 50 by 80 array. And in this case, the function is ID. It's a cheap function. Imagine here an expensive, very expensive computation. This will be our delete array, and we call compute as unboxed. So what the library is going to do is going to take this array and divide this computation among 7 cores that we have evenly. And it will load those chunks, row major fashion first, and whatever is going to be left over here, the little slack, the first core will be picking up. This is actually color coded by the core, so which core is actually doing the work. There are occurrences where computation of one element in the array is a lot more expensive than the neighbor, which would be kind of terrible here. Imagine like the bottom, the top part of the array is very cheap and the bottom is very expensive. Then the one core will be doing the most of the work, and that's bad. So for this scenario, we have a delayed interleaved array. It's easy to construct it. You just call to interleaved on any source array, on any array, and it will handle this unbalanced computation. You don't normally want to do it for balanced work because it's not too cache friendly. But for unbalanced, yeah, it's really nice. There is no example. A good example would be a Mandelbrot set. I don't have any pretty pictures created. And, hopefully at Zurich Hack in a few days, there's going to be some volunteers that will implement it, which would be cool. And compare the performance to available arrays, which would be even cooler. So here's how it's interleaved. So here is the same core is color-coded, but 1 by 1. And that's how we deal with unbalanced computation. Now, do we have any questions so far? Everything straightforward? Good. Slicing, it's a big part of the money. Oh, yes.
What's the performance difference between using delayed interleaves and just creating thousands of sparks?
I don't have that comparison, but it's a vastly different way to approach it. And sparks will work on box types, which are already slow, right? Yes. So if you compare parallelization of boxed, computing boxed array and let's say primitive array, it will be a significant difference in performance. Another part about sparks is comparison to massive. Whenever there is a scheduler behind the scene that is pinned to a particular core. So whenever it does interleaving in such a way, it will be, this core will use all of the cache that is possible. It is right next to it. Sparks, they will be computed in arbitrary order, whatever scheduler of GHCI does, and they are not pinned to a particular core. The scheduler, the worker that is doing the computation, it's not going to move from one core to another, so it's not going to lose its cache. So this gives it a huge advantage in performance. Does it answer your question? Cool. Where were we? So slicing. Quote from Wikipedia: array slicing is an operation that extracts a subset of elements from an array and packages them as another array, possibly in a different dimension from the original. In Massive, there is a support for slicing, as I call it, where you take an array, consider it a box, you take a slice. If you take a slice of a 3D array, you get a page. If you take a slice of a 2D array, you get either a row or a column. That's what the slicing is. Extracting will be taking an array and extracting any other rectangular part from it. So, you know, from this, extracting just a little portion from inside, but not two portions. They cannot be disjoint. All of the slicing is a constant time operation. There is not going to be memory allocation again, because that's expensive. All it is just index manipulation. So let's look at how that plans out. We create again our array, a three-dimensional array in this case. It's a 3 by 2 by 5 array. It's nicely printed. Now, if we want to take a slice out of it, let's take we want to take a page at the second index. It's technically a third page at the second index. We use this queued operator and we get this page. This I call slicing from the outside. We can change it, chain that operation. If we want to slice it even further, we want to take a first or column number first, number 1. Here it is. It's a second, not a column, sorry, a row. So you get a page, or you get a row with this outside outside slicing. We can do it from the inside, from the other direction. So if you want to, let's take, I don't know what we call it, this basically, it's kind of like a column, but it's a column in 3 dimension, right? Yeah, 3D column, there you go. It will give us that 3D column at the second index, and we can again chain it further, and we can get the column number 1 at index 1. 0, 1, 2, 1, 1, 2, 2, 1, 2. Here it is. We can also slice from within, which will make sense slicing in many dimensions. It's kind of pointless to think about it for flat vectors or 2D matrices, but already with third dimension we can slice, give it a dimension that we're interested in. So we have first, second, third dimension. This is going to be slicing at the second dimension at a 0 index, and here it is. And if you squint enough, we get 0, 0, 0, 0, 0, 1, 0, 0, 2. We get this row, we get this row, and we get this row. Whew. There is certain property that it holds, like slicing from the outside. It's the same as slicing at the highest most dimension. Slicing from the inside, it will be slicing at the very first dimension. I think it's more intuitive. There is a slicing implemented in REPA. For the longest time I tried to understand it. It's cumbersome. I had to do it at some point. By the way, at any point whenever I compare it to REPA, I want to say that I really enjoyed working with that library. I learned a lot from it. And the only reason why I started working on this library, because I found limitation in REPA, and it looks like it's no longer that well maintained, unfortunately. So that's why this library came into existence. Here's the slice, and that's slicing and indexing is partial. Whenever we slice out of bounds, okay, we get an error. We hate partial functions in Haskell. That's why we have functions that can do safe slicing. We'll do bounds checking. It will return nothing if it's incorrect. That's what the question mark will stand for. Well, maybe. And we can just as well chain them, slicing from the outside safe. This is sliced from the outside also safe, but it will take a maybe array. Yes?
Can we do stuff like in pandas with data frames where we would just slice every column that has a sum of something?
Ooh, nice. That's a good question. There is a part of your question is requires a filtering kind of operation, right? That's very tricky to do, and I don't have support for filtering in massive. It's kind of hard to do it in many dimensions. That's the reason why. You can do it in, let's say, vector has a nice support, and I could do it by the means of vector for flat vectors, let's say. That requires stream fusion, which we don't have here, and yeah, it's basically multidimensionality kind of screws filtering around. That's the answer. I do hope I come up with some point with a solution for this, and it would be nice to have. To continue on slicing, yes, we have the one that returns a just, which is the correct one. Same example as before, just safe. Now, here's the interesting part. We do a slice at the second page of index 2, row number 1, and element number 0, and we get an element. So we can slice all the way down, and it will be the same as actually doing an index at this particular index. This exclamation question mark is the safe indexing function, the regular indexing what we used to. So it's essentially the same thing. But remember I said that we cannot index delayed arrays. Well, you can slice delayed arrays because it's also just index manipulation, but you cannot index the very lowest dimension. You cannot slice it. You'll get a compile time error here. See, this is a delayed array. Oh yeah, sorry, I skipped the top part. We have a manifest array. Manifest is another representation. This is essentially any mutable array which loses its information, its mutation information. It's still represented by the memory, but you can no longer mutate it. You can still do constant time indexing. And that's why you can also still slice it. Its main purpose of its existence is to do this efficient slicing. We do a slice here of the, and we get back. You see this M representation, a manifest representation. It's kind of maybe a little bit confusing because there is a manifest type class and there is also a manifest representation. But essentially, it's just any arbitrary mutable array. And there is this function toManifest that will allow you to convert those to manifest. There is a possibility of extracting, as I mentioned before. It's the same with 3 by 2 by 5 array, and we do an extract of a subportion of it. We start at index 111, and the result array will be 2 by 1 by 3. And we get back again the 3-dimensional array with these 2 pages in it. If we do want to lower the dimensionality, by the way, we can apply a slice to it and it will lower the dimension. The great part about this resize extract slice pattern is we can chain those operations, and we can chain them magnetically. If it looks too complicated, don't worry about it. It's just demonstration purposes only. But here we do a slice, which is a safe slice. Then we go ahead and do an extract, and then we resize it. And we get a totally different array, which has all of its elements as a portion of the source array, and it all is done all in safe, constant memory, all just index manipulations.
I have a question.
Yes, go ahead.
On some of the earlier slides, you said that slicing and extracting is constant time. if there's no computation or something, the computation you mean there's some kind of compacting the array, or because I'm comparing with say vector, where extracting is actually always constant time. Though if you want to compact the
yes,
then you pay for that. So I'm wondering how.
Great. This is exactly the last bullet point on the slide. And I'm glad you reminded. I almost skipped over it. Whenever you have a big chunk of big array. It takes a lot of memory. You do a slice out of it. Now you're only interested in a very small portion of it. But you still have all that memory laying around, and a garbage collector cannot collect it because there is still a reference to it. So it is good. It would be a good idea in this kind of scenario to do a convert or a compute source, which will essentially create a smaller chunk and copy only the elements it's interested in. Another point is whenever you have a slice and this sort of chained operation like here, if you try to index this resulting array, it will be constant time indexing, but every time you do an index, it will have to do the index manipulation in order to figure out where this part is in memory every time. So if you're planning on reusing this array many times, it will be a good idea to go ahead and call compute on it. And the type classes, the way they structure, they will prevent you from doing anything wrong or stupid. So if it compiles, it should work, and it should work fast. At least in theory. Now let's talk about folding. Everybody knows folding. Everybody loves folding. It's the bread and butter of functional programming. We take a function range, which takes a computation strategy, a starting index, starting element, and the size, which is actually a range function, gives you from elements from 0 to 9. There is helper function like range step and stuff like that. Then once we call sum, it will do the computation in parallel, which is really cool. You don't need to worry about any of that. Another cool part is range will create a delayed array. So whenever you fold over it, you never created any allocation for your array at all. It will just create a tight loop and go over it, sum all those elements in parallel. It does it extremely fast too. There is lost it. There you go. There is a fold mono, which works on monoids. There is fold semi, a few other fold functions. There is a fold function, which I'm not really fond of, just because it has documentation a constraint that E is supposed to be a neutral element and associative with respect to this folding function, which is essentially a monoid. So fold mono would be a better suited folding function. There is fold ls, which is most common what we use to fold L. Left fold, there is fold right. There is the S star part stands for sequential. The reason for this is it's trickier to fold in parallel. That's why we can do that, fold mono of sum in parallel, because sum is monoidal. There is an empty element, 0, and there is a sum operator, which is a monoid. This is actually a definition of reduce. Whoever is from distributed computing, map reduce paradigm, reduce, you can do a fold only if it's a monoid. And that's why we can parallelize. And that's exactly also the reason why we have a separate function for structural fold, which is you can see from the type signature, it's a structural fold. We can see a direction left and we can see a direction right. And we cannot automatically parallelize those. As I mentioned, there is no memory allocation, and yeah, exactly what I told. For that reason, we have fold RP, which allows you to do a structural fold in parallel as well. The only restriction that we have to follow is we have to give two folding function. One to fold over those chunks as I was showing you in the picture, the one that will be distributed. Yes. Oh, 5 minutes. And there is a second folding function that will be folding the results of it. Here is an example of folder RP used on the array. This is a crucial part of the library that is not implemented at this level in any Haskell package. It's an arbitrary stencil. How many of you know what a stencil is? Okay, good. I was hoping nobody knew it. Just kidding. Many of you, I'm sure, have seen for loops like that, nested for loops. A stencil is essentially a way to describe this inner part. An inner part, this is what this code will do is iterate over a two-dimensional array and compute an average of its neighbors in a Moore neighborhood, all of the 8 neighbors around any particular element. In massive, it's the crucial part here is this to do. To do, you have to do bounds checking at the border. If you do it inside of the loop, it's going to be extremely expensive. It's the same essentially code, but written in Haskell in a pure functional way. You construct a stencil, and you create a function that can operate on an array without knowing where it is inside of the array. It only can index in relation to its neighbors. As you can see, you index -1, -1, -1, 1, right? Okay. And this gives us a huge advantage in performance. If you don't know what a stencil is, here is the Conway's Game of Life implemented in just a few lines with a stencil. Yeah, there it goes. Right? Have you seen this? The first time I implemented it was here in Warsaw, actually, in C. It was a lot longer than this code. I have, after this, I have a bunch of benchmarks. They will require a lot more time. I've been told that I'm running out of time, so.
You can always go down and sit over there and bring something and you can show them.
Okay. Let's see, do we have any questions? Maybe if you don't have any questions, I'll show one slide about benchmarks. Yes, here's the delayed array, by the way. There is a separate function that does computation around the border, and separate for the inside that does no border checking. That's how it goes really fast. Benchmarks, there's disclaimers. Here's a simple computation. We'll do a sum of 320,000 numbers. This is sum of doing of lists. This is sum doing with vectors. This is sum with repar and massive sequentially. They're all exactly the same. This is because of the fusion. In each library is different fusion. There is no allocation. They're exactly the same. There is a parallelization, repa and massive. Repa is a little bit faster just because it has a little simpler scheduler. LLVM gives some benefit. So it's safe to use LLVM with both massive and repa. Now here is the part. The long bars is the performance of repa. And this is summing arrays that are actually represented in memory. So that's where the indexing and everything that I've talked about so far boils down to. The bottom one, that's done in C. Let's see if you do the same operation in native C. This is just a zoomed in part. This is done with vector, storable, and this is done with massive, storable. Okay? And this is done with repa, storable. This is just zoomed in version of the previous one that does the computation of the same sum. Now, sum is not particularly computationally intensive. If we do stencil, repa has a very limited stencil computation, which is only convolution. And you can implement average using convolution. So here is again RIPA stencil and massive stencil sequentially. And this is RIPA parallelized on all cores, and this is massive parallelized. So sequential convolution with massive is faster, twice faster than with RIPA. And the RIPA convolution was a breakthrough. They have a few papers published about it, and which I studied and took some really good ideas from it. Compiled that with LLVM, gives huge performance for RIPA, a little bit less for massive, but still a performance. Sobel operator, it's also stencil, pretty much the same pattern. Massive is twice as fast as RIPA. Now, there is also a comparison with Accelerate. This was a last minute done benchmark, so take it with a grain of salt. But I was pleasantly surprised. I expected Accelerate beat Massive by far. In parallel, actually, the same Sobel operator is actually Sobel gradient is twice slower than with Massive. It is faster sequentially for some reason, probably because of the scheduler somehow. And it is a lot faster. Give me 1 second. Sobel horizontal. Oh, sorry, that's a sum. That's why. And the Sobel horizontal stencil is much faster in massive. So that's, I guess, sums it up. We get a very fast manipulation array library. We get efficient slicing, manual fusion, directional parallel folding, which nobody has, and fully featured stencil support. And it's actually really easy to use, but that's my opinion. You go ahead and use it and tell me all about it. I'll be really curious to hear your opinion. So that sums it up for me.